Hello and welcome to today's revision session on materials, which is part of the AQA A-Level Physics specification. So the first topic we're going to look at in this revision session is the bulk properties of solids. So the first bulk property of a solid you've got to be aware of is the density of a material. Now density is the amount of matter in the substance in a certain volume. So density is a measure of how much mass of material there is in a certain volume. So you could describe density as a measure of the number of particles in a certain volume, or a measure of the space between the particles in a certain volume, or a measure of how spread out the particles are in a certain volume. So if an object is very dense, it has lots of particles per unit volume, so therefore it has small gaps on average between the particles in the substance. Now if an object is not dense, then it has few particles per unit volume. So if an object is not dense, there are large gaps on average between the particles in the substance. So density is the mass of a substance in a unit volume, and this can be calculated with the equation density is equal to mass over volume. Now we tend to give our mass in kilograms, our volume in meters cubed, and therefore our density will be in kilograms per meter cubed. So we can argue that density is the mass of 1 cubic meter of a substance. So for example, gold has a density of 19,300 kilograms per meter cubed. So this means that 1 meter cubed of gold has a mass of 19,300 kilograms. So we can symbolize our equation with the following: rho is equal to m over v. Now just to clarify, you could write out your unit of density as kilograms per meter cubed or kilograms at meters to the -3. Either way is fine. Now always remember the unit of density is going to be written as the unit of mass divided by the unit of volume. So it's also fair enough to give your unit of density to be grams per centimeters cubed. So in the following example we can see that this will be grams per meter cubed, grams per centimeter cubed, kilograms per millimeter cubed, kilograms per centimeter cubed, kilograms per meter cubed, and kilograms per kilometer cubed. So you can see how you would work out your unit of density. So in the density equations, sometimes it's easier to change the units to suit the existing mass and volume units as opposed to trying converting. So like we mentioned just previously, the unit of density depends on the units of mass and the units of volumes used in the question. So you use these values to work out the density. So when we consider our density of an object either being very dense or not very dense at all, we can link this into the states of matter. So we can say that solids have a higher density than liquids, and liquids have a higher density than gases since they have more particles per unit volume. Or you could argue that solids have a higher density than liquids, and liquids are higher density than gases since there's a greater space between the particles per unit volume for your gas as opposed to your solid. Or you could say that in a liquid it is more dense than a gas because the particles are less spread out. So this shows the idea that solids have a higher density than liquids and liquids have a higher density than gases. So also just remember that technically a vacuum has a density of 0 kilograms per meter cubed, as there are no particles in the volume at all on average. Now the density is the amount of matter in the substance per unit volume, but it also determines if an object floats or sinks or not. So if an object has a higher density than the fluid it is in, it will sink, but if the object has a lower density than the fluid is in, it will float. Now water has a density of 1 gram per centimeter cubed, and this can be used to determine if a material will float or if it will sink. So we know that water has a density of 1 gram per centimeter cubed, so this means that 1 centimeter cubed of water has a mass of 1 gram. So let's look at an example calculation to work out our density when you're given the mass and the volume of a substance. Now if the shape is regular, it's a symmetrical shape, we can find its volume by using one of the equations you found in mathematics. So the volume of a sphere is 4 over 3 pi r cubed, the volume of a cube is L cubed, and the volume of a cylinder is pi r squared h. Now we can then use this to work out the density of a regular shape by doing density as mass over volume and working out the volume from one of our previous equations, and then as a result working out our density. Now densities can be very useful to identify materials in the real world, because if you have an unknown solid substance in a material or object, you can use the value of density to identify the material, because every solid material has the same density regardless of object dimensions. So if you can calculate the density of a solid material, you can work out what the material is. So for example, every material has the same density regardless of object dimensions, so aluminium always has a density of 2.6 0.64 grams per centimetre cubed regardless of the shape the object is in. Now you've also got to be able to work out the density for objects which are either regular or irregular shaped. Now regardless of the shape of the object, the mass of the object is measured with a balance. Now we can then work out the density of a symmetrical object by considering the shape it is in. So if you consider a 3D symmetrical shape such as a cube, but you can do this for any regular 3D shape, to calculate the volume you would then need to measure the different lengths of the cube, and then you'd use an equation to therefore work out your volume as shown here, and use the equation density as mass over volume. But if you've got an irregular shaped object, whilst measuring the mass is the same methodology, measuring the volume is slightly different, because to find the density of an irregular object we can determine its volume using a method called water displacement. So you put the object in a measured amount of water and measure how much the water level rises, and the difference between the two is the volume of the object, and therefore we can then calculate the density of our object. So consider a beaker of water, place a measured object in this beaker of water, and this object will displace its own volume in the actual water in the beaker. So it will cause the water level to rise, and the volume which the water level rises is the volume of the object, and the change in the water level of the liquid gives the volume of the object. You observe this effect when you get into a bath or you put dishes into a sink full of water. So for example, a beaker of water is at 300 mils without the object and 500 mils with the object in. So we have an increase of 200 milliliters or centimeters cubed, so that is our volume of our object, and then we can therefore work out the density by doing density as mass over volume and working out the density value of the object in this particular way. Now, it's also important to note that we will measure our mass with a balance as always. Now, alloys must have their density calculated slightly differently. This is because alloys are a mixture of two or more metals. So whilst the volume of a substance is not affected by the mixture of different particle types, the actual mass is affected. So we've got to consider the density of the two different types of metals. So let's have a look at an example. For an alloy of volume V with two metals, metal A and metal B, we consider the volume of metal A to be VA and the mass of this particular metal to be rho A times by VA. Now this comes from the equation mass is equal to density times by volume. We can then consider the volume of metal B to be VB, so therefore the mass of B to be rho B times by VB. So therefore we can use this to work out the density of the alloy by saying density is mass over volume. We can then say rho A times by VA plus rho B times by VB over V is therefore going to equal rho A VA over V plus rho B VB over V. Now V is the total volume of the alloy, and rho A VA plus rho B VB is the total mass of the two metals. So let's have a look at an example calculation. So we can calculate the density of brass, which is an alloy, by carrying out the following calculation. You use the equation mass is equal to density times by volume to work out the mass of the copper and the zinc. You can then add the two values together to get your total mass together. You then add the two volumes to get the total volume of each other. Then you can do density as mass over volume. So you do your total mass divided by your total volume to get your density out. Now, the next thing we've got to consider is that a resultant force can cause an object to change shape. Now, this is called material deformation, and there are three types of material deformation. You can have extension, which is when an object increases in size due to a force being placed on it. Now, a force which causes an extension is called a tensile force or a tension. Now, again, please remember that when a tension is applied, you get an increase in length. Now, for this to take place, you've got to have more than one force applied on the object, because this is a resultant force. Now you can also get a resultant deforming force to cause an object to decrease in size, which we will call a compression, and is caused by a compressive force. Now again, because this is a resultant force, you need at least two forces on the object to cause this to take place. And the third type of deformation is the idea of bending. This is when an object does not change its overall size, but it changes its shape. It is distorted. Now once again, you need a resultant resultant force to carry this out, so you've got to have more than one force acting on our object. Now there are two ways in which an object can behave if an object has a resultant deforming force placed upon it, regardless of its extension, compression or bending, and as an object can act as either an elastic or an inelastic. Now an object is elastic if the object regains its original shape after the forces deforming it are removed, whilst an object is inelastic if the object does not return to its original shape if the forces deforming it are removed. Now sometimes we will call this behaviour plastic behaviour, while we prefer to use the term inelastic to prevent confusion with the chemistry definition of plastic, which tends to be a polymer. Now many objects have an elastic region and an inelastic region depending on the size of the deforming force being placed on the object. So with lower forces, objects tend to act as elastic, whilst at higher forces objects tend to act as inelastic. So many objects will exhibit elastic behaviour at certain deforming forces and exhibit inelastic behaviour at large deforming forces. Now Robert Hooke was the first scientist who examined elastic materials by placing a deforming force on them, and he observed the following ideas. Number one, the greater the deforming force placed on the material, the greater the material extended. There were some materials that this relationship was directly proportional. When the deforming force doubled, the extension doubled, and finally with a large enough deforming force, the material will snap and break. So just to clarify, the deforming force is causing an extension. So in this particular case, extension is measured as the difference between the original length of the material and the length with the deforming force placed upon it. So we can clarify extension is the change in length of the material, or as we'll call it now, delta L. Now we give the original length of the material the symbol L. So therefore our extension is length with a deforming force minus length with no deforming force. Now extension is measured as the difference in length between the object with a deforming force and without a deforming force. Now it was found that the greater the deforming force, the greater the extension of the object, which would also be the case if we were looking at compression instead of extension. Now in fact, extension and deforming force increase at the same rate. They are in direct proportion, which is what we call Hooke's law. So when Hooke plotted this relationship, he achieved a straight line trend in his graph. Now an object is in its elastic phase when the graph is a straight line. Now the straight line section through the origin tells us that in this case force and extension are in direct proportion, because a straight line through the origin always indicates the two factors are in a directly proportional relationship. So if the force extension graph of a material is a straight line through the origin, it obeys Hooke's law, the object is elastic. Now the graph has to go through the origin, because when the deforming force is 0, the extension is going to be 0. If not, they probably haven't measured the extension, rather they've measured the length. Now Hooke realised that if a large enough deforming force was placed on the material, then eventually you would reach a point where force and extension no longer act in a directly proportional fashion, and the point at which this occurs is called the limit of proportionality. Now this point is also known as the Hooke's law limit. Now Hooke also realised that if you place a large enough deforming force on the material stops exhibiting elastic behaviour and starts exhibiting inelastic behaviour, and this is called the elastic limit. Now the elastic limit of a material is the point beyond which the material will become permanently stretched. So it's the point where it becomes permanently deformed. When all of the force is removed, the material will no longer be at the starting length, it will have been deformed. Now for most objects, the elastic limit and the limit of proportionality are not at the same deforming force. In a typical material, the limit of proportionality occurs slightly before the elastic limit. So you can see this in our following graph. After the elastic limit, a material starts to act like an inelastic, and then eventually, if the material has enough deforming force placed upon it, the object will snap and break, which is what we call the breaking point. Now the gradient of the force extension graph is called the spring constant. Now we know a resultant deforming force should cause an extension, so therefore the line should go through the origin. If it does not, like we said before, the experimenter has probably measured the extension, rather they've measured the length. Now just to clarify, what do we mean by spring constant? Spring constant is the amount of force needed to extend an object by 1 meter. It is how stiff an object is. Now the stiffer the object, the larger the spring constant. The stiffer the object, the more difficult it is to extend. So the spring constant can also be referred to as the stiffness as constant. Now the spring constant can only be taken in the straight line section of the graph, because if the gradient is constant, then the spring constant will be a constant. So the spring constant can only be measured when the material exhibits elastic behavior. Now just to clarify, the spring constant is not the same as the spring modulus, which is only considered in A-level mathematics. Now we can use Hooke's law to define the spring constant and the deformant force. So Hooke's law states that the force needed to stretch a spring is directly proportional to the extension of the spring from its natural length up to the limit of proportionality. So it means that the greater the force applied to the elastic object, the greater the extension of the object, as we can see in the following pictures. Now we can also work this out mathematically by stating the equation that deformant force in newtons is equal to spring constant in newtons per meter times by the extension in meters. So we can write this as F is equal to K times by delta L, but this equation only applies up to the limit of proportionality. This equation is obeyed by wires and solid objects which make up most materials. Now just to clarify, this equation is used for both compression, where delta L is a negative, and extension, where delta L is a positive. So we can actually work out values using Hooke's law as shown in the following example. A vertical steel spring fixed at its upper end has an unstretched length of 300 millimeters. Its length is increased to 385 millimeters when a 5.0 Newton weight is attached to the lower end. It is at rest. So the spring constant is therefore going to be extension. It's going to be 385 millimeters minus 300 millimeters. So it's 85 millimeters, which we convert into meters. We then say spring constant is the force over the extension to get 59 newtons per meter. Then the length of the spring when it supports an 8 Newton weight at rest. Well, it's important to note that the spring constant will be constant, so it's the same value for the previous example. So we now say extension is force over spring constant, so it's 8 over 59, so it's 0.316, but that's the change in the length from the original. So you've got to add on the original length to find the total length of the spring, which is 0.436 meters. Now, what happens if we placed our springs in series or parallel to each other? Now, if we place the springs in series to each other, which is a bit like one after the other, which is like electrical circuits, or you can have them parallel, which is when the springs are attached side to each other, a bit like being parallel in electrical circuits. So we can calculate the overall spring constant when the springs are placed in series, because we know that the tension in each spring is the same and equal to the weight exerted. So you know that extension, which is delta L, is going to be F over K. Now we know the total extension is the extension of 1 plus the extension of 2 as they're linked next to each other. So we can say that F over K1 plus F over K2 is equal to F over K. Now F is a common term, so it can cancel through. So we can say 1 over K total equals 1 over K1 plus 1 over K2, which is the same mathematics as working out electrical resistance in parallel. So therefore we can work out what the spring constant would be in a series with the following equation. Now it's important to note that the total spring constant of the two springs is lower than the individual spring constants of each, which is why it's not common to see springs arranged in a series pattern. Now we can also calculate the overall spring constant when springs are placed in parallel. So when a weight is supported by two springs in parallel, we can say that the extension delta L of each spring is going to be the same. So we know that F equals K delta L, so we can therefore say that with W is the weight of the supported by the two springs is equal to F1 plus F2. We know that K1 times by delta L plus K2 times by delta L is going to equal to K times by delta L. So delta L, our common term, can cancel through. So we can then say total K is equal to K1 plus K2, which is the same mathematics as working out electrical resistance in series. So you can see here an example calculation of working out the total spring constant when you place two springs in parallel with each other. So the total spring constant of the two springs is the sum of the individuals, so it's a higher value, which is why it's common to see springs arranged in a parallel pattern. Now we can also calculate the energy stored in an object exhibiting elastic behavior with a force extension graph. Now, like we showed previously, for an object exhibiting elastic behavior, the deformant force and the extension it causes are directly proportional. So it produces a straight line going through the origin for our line of best fit. So for an object obeying Hooke's law, the energy stored by the stretched material is equal to the work done on the material it is stretching. So we can say work done is equal to force times by displacement, but as you can tell from from this force extension graph, the deformant force is not constant, it's increasing constantly. So we've got to use the average force instead. So we know that if our force starts at 0 and our final force is F, the average force over this particular point is going to be a half F. So we can then substitute this into the equation and say work done is equal to a half times by F times by delta L, which is in fact the area under the line of best fit, because you can see that the area under the line of best fit is in fact a triangle, and it's going to be a half base times height, which is a half times by F times by delta L. Now this elastic potential energy is stored in the stretch spring. Now the elastic potential energy can therefore suddenly be transferred into the kinetic energy if our spring is suddenly released. Now remember, the work done on the spring is always stored as an elastic potential energy store because it's acting as an elastic object. So as this is an elastic object, Hooke's law is being obeyed, so that F is equal to K times by delta L, and we can substitute this into the value of the work done equation to work out another equation for work done, and say work done is equal to a half times by K times by delta L squared. Now if the material is stretched beyond the elastic limit, the work done, some work is done in changing the position of the atoms, so this will not be stored as elastic potential energy, which will be later transferred into kinetic energy. So when an object is inelastic, these work done equations cannot be used. Now please remember that the work done, elastic potential energy stored, is the area under the line of best fit for a force extension graph. Now whilst the force extension graph can be measured for a steel spring, the same can be true for a rubber band. So here are some sample results gathered for a rubber material. So does this rubber obey Hooke's law, and could you calculate the spring constant for rubber? Well, the rubber doesn't obey Hooke's law because the line of the force extension graph is not straight. So the force and extension are never directly proportional. So since there's no straight line section of the graph, there's no possible section on your graph to calculate your spring constant. But the area under the curve still does show the amount of elastic potential energy stored in the rubber band. So to calculate your area, you can count the squares of your graph or split the areas into different shapes or integrate the equation of the line. So we can consider the force extension measurements for loading a rubber material with weight, placing weights on the material, and unloading the rubber material with weight, taking those weights off that particular material. So our blue line shows the results for loading the rubber band, and loading material is when the deformant force on the material is increased. The red line shows the results for unloading the rubber band. Unloading material is when the deformant force on the material is decreased. So you can see our two lines showing loading and unloading. So this shows that the rubber band is an elastic object as the object returns to its original length when the deformant force placed upon it is removed. We can see this because the two lines meet at the origin. Now again, the rubber band shows that there's different properties when loading the rubber band compared to unloading the rubber band. So that's important because in this process, the loading process has inelastically deformed the material, which has caused a difference between the loading part, which is elastic, and the unloading part, which is inelastic. Now if you notice on the particular graph, the blue line has a greater area under the curve, so there's more elastic potential energy stored when you are loading the spring. Now the red line, the unloading line, has a smaller area under the curve, so less potential energy is stored in our spring when it's being unloaded. So this produces different areas under the curve for each line, which indicates there's a different amount of elastic potential energy stored in the material between loading and unloading. So there's less elastic potential energy stored in the material when unloading compared to loading. But why is this? Where is some of the energy gone? Now the difference in energy stored in the rubber band is due to some energy becoming internal energy of the molecules, because you can see how particles interact in a material when it's acting elastically. So if an object is acting like an elastic, when it is put under tension or compression, the atoms of the material are pulled apart or pulled together, but because they're only moving small distances relative to their equilibrium position without actually changing their position in the material. So once this load is removed, the atoms return to their original equilibrium distance apart. The material is still obeying Hooke's law in acting like an elastic. But if you look at what's happening afterwards when it's been inelastically deformed, there's a difference, because if the deformation is inelastic, the material is permanently stretched even when the force is being removed, because some atoms in the material move position relative to one another. So when the load is removed, the atoms don't return to their original position because the material has been stretched past its elastic limit. So the stretching effect makes the molecule molecules absorb energy and start to vibrate faster. So this increases the internal energy of our rubber band. The energy is changed store and work is being done. So the internal energy of the molecules increases, which increases the temperature of the rubber band. Work is being done by the rubber band. So you can see the elastic potential energy stored when the rubber band is being loaded, and the elastic potential energy stored when the rubber band is being unloaded. Now the difference between the loading areas under the curve and the loading area under the curve is the work done by the rubber band, and this work done is being carried out to rearrange the atoms of the material, and this makes energy transferred to the thermal energy store of the object and its surroundings. Now we use this in many examples, such as the crumple zones of vehicles as they inelastically deform when during a crash, so less energy will be transferred to passengers. Now you've considered the force extension graph of a rubber band. Now just remember, our unloading line goes through the origin, and the rubber band therefore returns to its original length, and the area under the loading curve is the work done to stretch the rubber band. So the area under the unloading curve is the work done by the rubber band unloaded. So the area between the loading and unloading curves is the difference between the energy stored in the stretched rubber band and the energy recovered when unstretched. So the difference between the energy stored and the energy recovered is because some energy is transferred to the internal energy of the molecules. Now let's now consider a force extension graph of a metal wire. Now you'll notice that the unloading line does not go through the origin because the wire has been permanently stretched. So the area between the loading and unloading lines is the work done to permanently deform the wire. Now you'll notice that the loading and unloading lines are parallel to each other, as the bulk properties of the metal, the spring constant in this example, stays constant. Now finally, you've got to be aware of the force extension graph for a plastic strip. Now the unloading line does not go through the origin. This indicates to us that the plastic strip has been permanently stretched. It is now acting inelastically. Now the area between the loading and unloading curves is the sum of the work done to deform the strip, and the energy is transferred to the internal energy of the molecules. So we've looked at the bulk properties of a material. Let's now look at the Young's modulus of a material. So as we mentioned before previously, there are many properties of a material you can work out from its force extension graph. Our gradient is the spring constant or the stiffness, and the area under the curve is the energy stored in a material due to deformation. However, the concept of stiffness and force extension graphs change depending on the dimensions of the material, because the amount of deforming force that needs to be applied to cause a particular extension is dependent on the dimensions of the material, and vice versa for the extension. So this tells us that the gradient, the stiffness of the material, is dependent on the dimensions of the material. So we should actually try and find a better quantity that represents the stiffness of a material but does not change on the based on the dimensions of the shape. Now this is achieved not by looking at a force extension graph, but rather by looking at a stress strain graph. Now stress is the amount of is something applied on a material which can be considered independent of the dimensions of the material, and strain is again produced by a material but is considered to be independent of the dimensions of the material. So our gradient of our stress strain graph, our Young modulus, is in fact independent of the dimensions of the material. So it's very important to note this, that the Young modulus of a material is consistent regardless of the dimensions of the material shape. It's an absolute material quantity. So the Young modulus can be calculated by measuring the stress and the strain of material, and we know that the Young modulus is stress over strain. So we can use this as a measure of stiffness of a material. So it's used by engineers to make sure materials can withstand sufficient forces in different situations. Now stress is therefore a more absolute and fundamental quantity considering force, and strain is a more absolute and fundamental quantity considering extension. Now the tensile force is the force applied on a material when considering the area over which it is applied to. So it can also be referred to as the deforming pressure acting on an object. So the tensile stress is the pressure a material is under, so it's the force per unit area. So stress in newtons per meter squared or pascals is equal to force in newtons over area in meter squared. Now once a material is put under stress, it will show a strain. A strain is a measure of how much a material has extended based on its original length due to the stress that was acting on it. Now it doesn't matter if the forces are compressive or they are tensile, because either one can cause a strain. So stress pulling on a wire causes strain, and strain is a ratio between the original length of the material and the amount it has extended by. Now strain has no units because the two units of length will cancel through each other. So strain is equal to extension in meters over over original length in meters. Now, as we know the Young's modulus is an absolute measurement of stiffness, we can work it out based on our prior knowledge. So we know that the Young modulus is stress over strain, and we know stress is force over area and strain is extension over original length. So we can rearrange this to make the equation for Young modulus to be force times by original length over extension times by area, and it has units of newtons per meter squared or the Pascal. It has the same units as stress because strain has no units, it's just a ratio. Now you can see that the stiffer the object, the higher its Young modulus. Now we can analyse the material further by considering a stress-strain graph. So we can draw stress-strain graphs as follows, with the gradient of the line as delta y over delta s, which is x, which is the stress over the strain, which is going to be the Young modulus. But you can only calculate the Young modulus as the gradient of the straight line section of the graph, because you can only calculate the Young modulus when the material is exhibiting elastic behaviour, when it is below its limit of proportionality, when it is obeying Hooke's law. Now stiff materials have a steep gradient because they have a high Young modulus. Now the area under this line is going to be a half times by stress times by strain due to the equation of half base times by height. So we can therefore say it's a half times by force over area times by extension over length. So our equation is actually going to be energy over volume. So the area under the line of a stress-strain graph is the strain energy, the energy stored per unit volume in the material. It's the strain energy in 1 meter cubed of the material. Now we can also look at the stress-strain graphs from many different materials, such as metals. So this is the stress-strain graph for copper. Now you'll notice that copper is a ductile material as it undergoes a high plastic deformation before breaking. We can tell this because there's a large non-straight line section to our graph. Now we can look at various different properties of a material from a stress-strain graph. The first such property is the ultimate tensile stress, which is the highest value of stress on the graph, which shows the maximum stress a material can withstand. Now it's important to note that we sometimes refer to this as the strength of the material. Now engineers have to consider the UTS when designing a structure. They need to make sure the stress on the material will not reach the UTS when conditions change. The next point we need to be aware of is the breaking point. This is the last value of strain on the graph. It's when the bonds between the molecules separate completely and the material snaps. Now once again, engineers have to consider the breaking point when designing a structure. They need to make sure the stress on the material will not reach the breaking point when the conditions change. So strong material should have a high UTS and a high breaking point. Now there's also the yield point on the graph, which is the point where the line dips, so it shows our material given. So it makes the material much weaker and can't withstand much stress. So at the yield point, the material suddenly starts to stretch without any extra load being added. So it's the stress in which a large amount of plastic deformation takes place with either a constant or reduced load acting on the material. So there's actually two sections to our yield point. You've got the weakening, which is when the material weakens suddenly and starts to stretch, and the flow, where a large strain is achieved. So you've also got on your stress-strain graph two other points, the limit of proportionality and the elastic limit. The elastic limit is the point where the material will no longer go back to its original shape after the force has been removed. Now the limit of proportionality is when the force and extension are no longer proportional. So for most materials it's not the same point. The limit of proportionality is slightly before the elastic limit. At the limit of proportionality, the material stops obeying Hooke's law but would still return to its original shape if the stress acting upon it was removed. But at the elastic limit, the material will no longer return to its original shape once the stress has been removed. Now a brittle material will have the following stress-strain graph. It'll still obey Hooke's law at lower stresses, so you observe a straight line through the origin, but when the stress reaches a certain point, the material suddenly fractures and it doesn't have much plastic deformation. Now examples of this include chocolate bars, glass and pottery. Now we can actually look at an investigation to calculate our Young's modulus from experimental values. So what you would do is as follows. You place two tables together, you'd retrieve the wire which is being tested and you'd have a pulley at one end and a G-clamp at the other and place that wire between the two. And you should try to have some excess of approximately 30 centimeters. Now you want to keep keep your length of wire in this investigation as long and as thin as possible, because an increased original length reduces the percentage uncertainty in the original length measurement, because our absolute uncertainty is constant, and secondly, an increased original length gives a more noticeable extension, which gives a greater range of results and a lower percentage uncertainty in the extension as well. You'd use a G-clamp and wooden block to trap your wire which is being tested so it doesn't slip out, and ensure that you would loop the excess wire over a pulley with a knot, because we're going to create a loop which will hold some weight on our particular wire. So we'd hang a 1 Newton weight in the loop to produce tension in the wire, so we define putting a 1 Newton weight on our material as given an extension of 0. We then use our hand to straighten out the wire and remove any kinks from our wire, and this process is repeated several times because we don't want our material to unwind during our investigation. Now, for safety reasons, you then place a carpet tile under the weight in case the wire snaps at any point. You then retrieve a screw gauge micrometer, and remember that this uses a vernier scale so you can read in the values of 0.01 millimeters, so it's more suitable when measuring the diameter of our wire. Now again, you should measure the diameter of the wire in many different places and then calculate an average. Now this should be carried out in various different places at random on the wire. Now when you're working on this, take care not to crush the wire with a screw gauge micrometer, and you may wish to use the ratchet to tighten your screw gauge even further, but always be aware that applying a deforming force on the wire could cause your diameter to change. You then place a ruler at the end with the G-clamp, and at the 30 cm mark place a marker on the wire with the sticky tape. You then place various weights on the loop and measure the new extension between the marker and the G-clamp. We use this to derive the extension of the wire from the original length. Now you should always wait about 10 seconds between placing the weight on the loop and then measuring the length. This is to account for creeping in the wire, which is when the material slowly plastically deforms when a tension force is placed upon it. Now when measuring the length of the wire, you should stand directly over the marker and wear safety glasses. Standing over the marker to take measurements reduces the impact of parallax error in your experimental results. Now also note that when the wire is taut, it is an elastic potential energy store, so if it snaps, this energy will transfer to the kinetic energy store and could possibly damage your eyes when it moves. So you should place 2 or 3 shields across the wire to prevent it moving greatly when it snaps. You should then measure the length and extension of the wire for various weights. You should then hopefully measure your diameter, convert it into meters, and then work out your area in meters squared. You should then work out your force supply by looking at the weight placed upon it to create a tension. You should measure the length of the wire with the ruler, measure the extension of the wire as talked about previously. You can calculate the area of the wire from your previous work, and then we can determine the stress by doing force over area and the strain by doing extension over original length. You would then draw a stress strain graph of your results, placing the stress value on the y-axis and the strain value on the x-axis. You then draw a line of best fit with error bars on your points, and shown as here. The gradient of the straight line section is our Young modulus. Now you can only determine the Young modulus when the material is acting elastically. You can only determine the Young modulus when the material is an elastic potential energy store. Now remember, when working this out, you draw your gradient triangle as large as possible, because this increases the validity of your results as you're considering more data in your value. So let's summarize what we've looked at in today's revision session. The definition of density is ρ equals m over v. We should know Hooke's law and the elastic limit, where F is equal to K times by delta L. You should be able to describe plastic behavior, fracture and brittle behavior linked to force extension graphs, have a quantitative and qualitative application of energy conservation involving elastic strain and energy to deform, and understand that the spring energy will transfer some elastic potential energy to kinetic and gravitational potential. You should also be aware that the Young modulus is tensile stress over strain, so it's F times by L over A times by delta L. And you should understand how to use stress strain graphs to find the Young modulus, and use one simple method of measurement to work out the Young's modulus experimentally. So I hope you've enjoyed today's revision session on materials, which is part of the A-level AQA topics that we cover. If you do have any questions, please do ask. Thank you very much for watching, and as always, have a lovely day.